Welcome to this explainer. Look, today we're tackling something that affects literally every single electrical technician stepping onto a modern job site. Think about it. A modern electrical installation isn't just a simple grid-to-load equation anymore. It's a high-stakes puzzle. If you walk onto today's sites relying on traditional assumptions, that complacency can literally be fatal. So we're tearing up the old rule book and focusing on the absolute necessity of safe practices when working with alternate supplies.
Okay, let's dive into this. What happens when the power you just cut isn't actually cut? Today's multi-directional grid means your life depends on knowing exactly what is powering a site. You throw the main switch, but the lights stay on. Or worse, the lines stay live. Why? Because alternate supplies are absolutely everywhere now. So here's our ultimate job safety analysis for today. First, we'll look at the new electrical reality. Second, the hidden dangers and risks. Third, building safe work systems. Fourth, the foolproof isolation process. And finally, securing the work area.
Section 1. The new electrical reality, a changing grid. Thinking about the traditional versus the modern setup brilliantly illustrates exactly what we've moved away from. Back in the day with a traditional setup, you had a single main supply. You throw one main switch, cut all the power, and boom, you get to work safely. But in a modern setup, you've got the grid plus solar PV plus battery storage and standby generators all tied together. Isolation is no longer just a single action. It's a complex, multi-layered procedure.
At the heart of all this complexity is the Inverter Energy System, or IES. You can think of these inverters as the ultimate traffic cops of modern alternate supplies. They're managing the whole shebang. They control grid exports, battery charging, and crucially, they decide when to supply power to a backed-up load if the main grid happens to fail.
Which brings us to a really critical concept, islanding. Islanding is essentially a situation where the grid supply fails, but an inverter or generator keeps pumping electricity to a section of the installation. Preventing these unintentional islands of power is an absolute key to maintaining your safety. If an inverter doesn't automatically disconnect during an outage like it's supposed to, you could be walking right into a live zone you thought was totally dead. No way you want to risk that.
Section 2. Hidden dangers and risks, and the invisible threats we face. We need to shift our perspective right now, because the invisible threats on a modern site can catch even the most experienced veteran completely off guard. If you take only one thing away from this explainer, let it be this. Treat all conductors as energized until proven de-energized. This is your absolute survival mantra. The biggest hidden danger isn't the complex wiring, it's complacency. You can't trust your eyes, and you certainly can't trust a switch position. You can only trust your testing.
Now, what's really interesting about this is that the hazards you face aren't strictly electrical. You've got unearthed PV arrays that can cause capacitive coupling, meaning the metal roof itself can give you a nasty shock, potentially causing a fatal fall. You've got incorrectly installed batteries presenting fire, explosive gas, and chemical hazards, and generators backfeeding through detachable connections. You are working in a multi-hazard environment every single time.
And when things are wired incorrectly, the results are terrifying. No switch or circuit breaker shall be inserted in the neutral conductor. Why is this hard and fast regulatory rules so crucial? Well, because if a changeover switch open circuits the protective earth neutral, the PEN conductor, the entire earthing system of the site, including the metal switchboard itself, can become fully energized. It literally turns the very safety mechanism of the house into a lethal hazard.
Section 3. Safe work systems and neutralizing these threats.
We've seen the terrifying risks, right? So now let's pivot to the calming, methodical systems we use to neutralize them. Everything starts with the hierarchy of control. Notice what sits at the very bottom. PPE. Personal protective equipment is your absolute last line of defense. The primary goal, way up at the top, is elimination. That means working on de-energized equipment. That is always the objective. You eliminate the hazard entirely before you ever rely on a pair of rubber gloves.
But what if you absolutely have to work on live equipment, like when you're testing for polarity? Well, working on energized equipment is only permitted under very strict specific circumstances. You need a competent person, properly tested tools, a formal safe work method statement, and usually a safety observer. These protocols are non-negotiable, folks.
Section 4. Foolproof isolation, the core procedure.
Let's see how this builds. Here is the critical chronological sequence for cutting off all power sources. And yes, that includes backup batteries and solar. Step 1, consult with the people on site. Step 2, do a thorough visual check for all alternate supplies. Step 3, actually isolate the equipment. Step 4, test to prove it's dead. And Step 5, secure the isolation so nobody can undo it.
I want to zero in on Step 4 for a second, the testing phase. This rigorous 4-step testing loop is your lifeline. First, you test your instrument on a known voltage source to prove the tester actually works. Second, you test between all supply conductors and earth. Third, between all supply conductors. Finally, and actually scratch that, this is where people get lazy, you have to retest the instrument on a known voltage source again. Proving your tester didn't break during the process is just as important as the test itself.
And while we're on the subject of testers, beware of proximity testers, or volt sticks as they're often called. They're indicating devices only. A surprising number of injuries happen because technicians trust these blindly. Do not rely solely on a proximity tester for life-saving isolation. It's a massive mistake. They don't always provide a reliable indication, and betting your life on one is a gamble you will eventually lose.
Section 5. Securing the area and preventing accidents.
So, the crucial point is that once you've proven the power is dead, you have to ensure nobody else accidentally reverses the safe environment you've just methodically created. If you don't have sole, effective control of the isolation device at all times, it must be physically locked off. You need built-in locks or lockout jaws. And importantly, every individual worker on the job applies their own personal lock. It also needs to be sturdy enough to withstand vibration or someone inadvertently bumping into it.
Right alongside that lock goes a danger tag. These are literal lifesavers. They've got to be red and black on a white background, dated and signed by the worker. Crucially, they need to list specific hazards. If you're working on a modern site, writing something like multiple points of supply on that tag warns everyone else that flipping a switch could reconnect an alternate supply and endanger your life.
But what happens if the clock runs out and the job just isn't done? Leaving unfinished work requires strict procedures. You must terminate and enclose any exposed conductors, secure the surrounding metalwork, barricade and tag the area, and hand over adequate safety information. You've got to ensure your unfinished job doesn't become a lethal trap for the family living there or the next tech who shows up tomorrow.
As we wrap up this explainer, I want to leave you with a final provocative thought. Are you betting your life on a visual check, or are you proving it with a test? Look, the electrical grid has evolved. Solar, batteries, and generators mean danger can come from absolutely any direction. Update your mindset, follow the isolation sequence, and always, always prove it's dead. Stay safe out there.